idea, right? What is electric potential and all that in a very short time. And then we can start with the worksheet. So what is a potential difference, Anvisha? If I ask you, what is potential difference?
The work done
Yeah. Yes. Let us suppose there is a point A and a point B, right? And you have to get a test charge and you have to move it from point A to point B, right? The test charge is Q naught. It has a very small magnitude of charge and you are moving it in an electric field from point A to B, right? So the work done, work done per unit charge, that is the potential difference between the point A and B. So how do we write? Can you tell me? How do we write if I have to find the potential between A and B? How do we write it? Is it VA minus VB or is it VB minus VA? Yes. So it's the final position, right? Final position is B and the initial position is A. So it will be VB minus VA, right? And what is the work done by the external agent, right? In moving the point from A to B upon the test charge Q naught, right? So that is the potential difference. And if I asked, like, give me the potential at a particular point A, right? So at this point A, then what we'll do? We'll consider the point B at infinity, right? So then VA will be when you are considering the point B at infinity. That is, you are doing the work from getting the charge from infinity to point A, right? So under that condition, let us suppose this is point A. I have considered this point B to be at infinity. I'm getting the charge from B to A, right? Now what will be VA minus V infinity, right? And the external work done by the external agent upon the Q naught, right? So we know it is an assumption that the potential at infinity is zero. So VA is equal to the work done by the external agent, right, upon Q naught. So that is the potential at a particular point P. So basic idea is like the potential difference between 2 points. If you know the potential difference, then you can find the potential at a particular point by considering the other point at infinity, right? So there are certain important points we should know while finding the potential, right, at any point. So first thing is that the work is always done against the electric force, right? And the charge Q naught is very small. It does not has its own electric field, so it does not have its own potential also. And the work done is independent of the path, right? So it is path independent. Like if you're moving a charge from A to B, you can get this way or you can get this way. It doesn't matter. It is path independent. So, right. So now there are certain proof which I won't go into that depth. You just tell me the expression. Let us suppose you have to find this is a a point charge, and you have to find the potential at this point P. So this is a point charge I've taken, capital Q, and you have to find the potential at this point P. So what will be the expression? K, the distances are. So at R, you have to, at point P, you have to find, so it is KQ upon R, right? So this is the potential due to a point charge. And if it is negative, this is a positive charge, and if it is negative, then what happens? This same expression will become minus KQ upon R. So whenever you're taking the expression of writing the expression of potential, you have to write the charge also, right? If it is a positive charge, it becomes plus Q. If it is minus, the expression becomes minus KQ upon R, right? And if there are number of, let us suppose, charges, this is Q1, Q2, Q3, and they ask you to find the point potential at this point P. So that, and the distance, let us suppose this is R1, this is from R2, this is R3. Then what will it be? the resultant, if let us suppose have to find at P, that will be the potential due to Q1, the potential due to Q2, and the potential due to Q3, right? So is this potential a vector quantity or a scalar quantity? Yeah, is it a vector or a scalar? I think your voice is not audible, Anvisha. There is some issue, I think, audio, right? Issue from your side. Okay, so no, this is a scalar quantity, right? So we have to not to consider any direction, right? In electric field, you remember when we had to find the point P, we are always considering in which direction the electric field rise, right? And then we take the cos component, the sine component, then we find the resultant electric field. In this case, it's just a summation of all the potential due to the each charges present in the system, right? So that was about the electric potential. Now let us suppose we have to work done. You have to find the work done in moving a charge from one point to another. So work done in moving a charge. And let us suppose that you are moving it from point A to B, the charge. So what will be that work done? So we know the potential is what? The final minus initial, VB minus VA, that is the external, the work done by the external agent. From A to B we are going upon the charge Q. So now you just cross multiply, you can get the external work done, which is Q times delta V. What is this delta V? The final position, at the final position, the potential, and minus the potential at the initial position. That gives you the work done. So this is also a very important expression. Using this, you'll be solving some problems. So that's it. Now they often ask you, like, let us suppose there is a ring, yeah, and positive charge is uniformly distributed at the surface of the ring, and they ask you find the potential at this point P, which is at distance R, right? And the radius of this is capital R. So in that case, there is a formula there. Actually, there is a proof also. The final formula that you get is the V potential at the axis is equal to K. Let us suppose the charge is capital Q in this ring. So it is KQ upon root over capital R square plus the square of this distance, right? So this is the final value of the potential at this point P. And if they ask find at the center, then you have to just substitute R is equal to 0. The distance reduces. So at center, it will come V center, let us suppose, the potential at the center. So you substitute the value, R will become 0. So it is KQ upon R, right? So this is an important expression. Same thing we had done in the electric field also, right? The electric field at the axis, what it was of a ring, we have got KQ R upon R square plus capital R square whole to the power 3 by 2, right? So these both expressions are important.